Hello everyone, welcome back to the class. This is a video for the first online lecture during the Chusok break. This is supposed to be the October 1st day class on graduate electromagnetism 2. Last time we talked about non-relativistic Larmor formula, and today we want to discuss the fully relativistic version, and I will follow half of my lecture based on the textbook, but at the other half I'd like to compute the power of the so-called relativistic Larmor formula based on Lorentz invariance of the formula as opposed to what was done in the textbook. You'll see what I mean by that. So let's try to move to the next slide. So it's gonna be a little faster than normal class because I already have written all the formula that I need. So the top title is the power radiated by relativistic sources. So for the computation of the power, we compute the Poisson pointing vector at the time t and the position x, and that's related with this formula. So originally it's 1 over mu 0 times E cross B. But B is 1 over C times R cross B for us. So we have extra speed of light coming down and electric field square, and the direction is R unit vector. And if you plug the electric field formula in, where the radiation part of the electric field is in this form, where we have in the denominator we have 1 over R dot phi power of 3, and if you have square of the electric field, so you have power 6 here, and then you have absolute value square for the numerator, whole thing, and you have numerical factors here. And if you carefully compute, you will be convinced yourself that this constant factor is indeed correct. So now we want to calculate the power. Power is the energy per unit time, but we want to calculate the power per unit solid angle. So it's going to be the energy over dt over the omega in terms of the unit. But this is the power at time t, so you can call that power to be the received power at time t. So we want to call that to be PR. R stands for the received power. So all you have to do is to put pointing vector, and you have compute the solid angle component and so on. So, and the direction, you have to take a normal derivative to the direction. So S in the product, R unit, and solid angle component goes to the left in the denominator, so you don't have that part. So you'll immediately see that this is the formula you're gonna get. The only difference is you have this R square, so this R square is disappeared. So now the real component that you have is right there. Now on the other hand, we can also think about not the received power, but the power emitted from the source at the retarded time. So we want to call that to be power emitted. So we have E as subscript. And we are interested in this PE, which is defined as dE over dt retarded. And how do we get this? you can compute this partial derivative of t retarded respect to the normal time t, then I think we have seen this before, and it's 1 over 1 minus r unit dot v retarded over c. So we have this, you have to revert this to get the relationship between emitted power in terms of received power. So you have this extra factor in. Okay? Now, we want to have this formula, this differential energy spectrum, and differential is over the time retarded. So overall the power retarded, and you want to do it in terms of solid angle. So that's the master formula you have. Because of the extra factor from retarded time, the power of 6 became power of 5. So this is, as far as the formula is concerned, this is what we call relativistic Lamé formula. But we want to simplify this by doing vector algebra. But that's tedious, so we want to do something fancier, which is utilizing the Lorentz invariance of this quantity. I'll briefly mention about the Lorentz invariance of this. So let's write, let's start with this dE over dt, right? Assuming this is a Lorentz invariant quantity. And if you take a look at the textbook, the Lorentz invariant formula for dE over dt ret is in terms of this complicated but a simple constant. Now I have 4 momentum Lorentz vector contracted with the index nu on superscript here and subscript, and then it's a differential with respect to the proper time. And such a discussion on this Lorentz invariant form is described in the text, so I skipped that part, but we would like to use this. So having this 4 momentum vector to be mass times 4 velocity vector, where 4 velocity vector is gamma c for the time component and gamma v for the 3-dimensional vector velocity vector format. And I remind you that proper time, the tau is dt over gamma. So we can plug all that in. So this gamma and that gamma is cancelled, so that we don't have gamma term and at the end, but dE over dt ret can be expressed in terms of constant times, and the mass is also cancelled with the mass in the 4 momentum Lorentz vector. And now it consists of only expression in 4 velocity vector. So now let's use this formula to compute the actual left-hand side. So the steps are quite involving, but I summarize this. I'll be moving fast, but you have to really sit down and confirm these steps. I hope this is correct. So U.0 is by definition, it's U0 is C gamma, and differentiation with respect to proper time. So I take out C here, and I move from proper time to the local time t. So I have gamma here, and then I have to differentiate with respect to gamma here. So C gamma from here is there, and gamma is square root of 1 over square root of 1 minus beta square. So we have minus 1/2 coming down, and 1 minus beta square, and I have to subtract minus 1 over 2 minus 1. That brings me minus 3 over 2. And now I have to differentiate the inside. So I have minus 2 coming down, so 2 beta in the product, and beta dot itself. So you can simplify this if you take a look at minus minus plus 1/2 factor 2 cancels. I have so 1c going cancelling with beta dot. Beta dot is v dot over c. V dot is acceleration, and c in the denominator cancelled with the c. So I have original beta coming here, and combining with this gamma and this vector, I have gamma power of 4. And spatial part, I have u vector dot, so that's this. Now I have two terms, differentiation going to gamma, so I have this term, and second differentiation going to v, so I have acceleration overall factor is gamma square. And we know how to calculate this d gamma over dt, because that's what we did here. So we have gamma power of 4 beta dot a, which is this guy, times beta. Here we have the first component with beta, and the second component is simply gamma squared times vector acceleration. So what we want to calculate, let's go back to the previous slide, and this is what we want to calculate, the time component of 4 velocity vector square with minus and plus three-dimensional u dot square that we all have. All you have to do is to use this to compute this. So we have this thing, full thing square with negative, so I have minus gamma power of 8 and this full thing squared. And I have spatial component. By squaring this is sum of 2, so I'm going to have 3 terms. So first term gives you this, gamma power of 8, beta dot a power of 2, and beta square itself. And the second term is gamma 4 times a square, that's this. And cross term is 2 times gamma 6, and beta dot a here, and beta dot a from the cross term, so I'm gonna get the square at the end. Excuse me. And you can reduce this further by taking out gamma power of 6. So I'm gonna have gamma square, and let's factor out beta dot a square. So I'm gonna have here gamma square. I also take out gamma square. So from the first term I have minus 1, and I have gamma 8 and beta square. So beta square comes here from the second term. And second term, the third term, which is this guy, gives me 2 times beta dot a square because I take out gamma 6. And plus, since I have only gamma 4, I have gamma power of 2 in the denominator and a square. Now, if you take a look, this beta square minus 1 is minus gamma square. Right. I'm wondering. Oh, okay. And then you can also combine with the others. If you have, so this is minus beta dot a square, and this is plus 2. So you have beta dot a square plus that. So these 2 terms will be the first term, and the second term goes like this. And then gamma square is 1 minus beta, inverse of gamma square is 1 minus beta square. And then you can reduce this in terms of So a squared is here. I have a square, beta square. It's negative sign. Minus is taken out. So it's plus inside. And I have beta dot a square. That's minus minus plus. So order sign is plus. So this one inside is nothing but beta cross a square by definition of beta cross a square. So you can reduce down all the way to here. Okay, we are almost done. So let's move to the final stage. So what we originally wanted to calculate is dE over dt. And our computation in the parentheses turns out to be this. Gamma power of 6 times this, whatever this is in the big square bracket. And you can take out, replace beta to v by taking out speed of light square, because this is a square. So any of this, one, top or bottom, which is basically in the textbook, this is the equation 10.156. And we did it in a different way, which is the fully Lorentz covariant method. So this is easy to explain, but for me, it took like, I don't know, 3 or 4 hours to derive this with various errors and mistakes and so on. Anyhow, this form is now called the relativistic Lamé formula. And using this identity that we already used, we could change to this dE over dt ret to be constant times the square term can be simplified to be this. You could verify it, which is appeared in 10.158 in your textbook. And we can also change v dot a in terms of v times scalar v times dv over dt. And this is 23 refers to small note in the textbook, which demonstrates validity of this formula, so that you could now have, instead of v dot a, you can have this formula as well. That's probably all I have for today. So it's kind of short lecture today, although the derivation took quite a while, so you have to calculate by yourself line by line. One last thing is, so this is, as I mentioned, this dE over dt ret. We used this in a relativistic manner, and this is actually Lorentz invariant quantity. You can prove it in a rigorous manner, and that is explained in the text, but instead of going through, you can sort of see why this is happening. The energy and the time both are so-called time component of Lorentz 4 vector. So this dependence of the tau, depending on which Lorentz frame you are in, is exactly cancelled for this quantity. So it's sort of easy to understand that this dE over dt ret is the Lorentz 4 vector. I mean, the cancellation is done in such a way that it's Lorentz invariant, because as I said, the gamma factor is cancelled out. Okay? That's all I have to say. Please make sure you follow all the steps and you understand this formula. That's all for today. Thank you and enjoy your Chusok.